Ladies and gentlemen, this is the Computer Programming University, where learning is always fun, as it should be. And tonight we're going to be taking part in a awesome lecture, Artificial Intelligence Conference, TensorFlow Machine Learning for Programmers, presented by Lawrence Maroney. As you guys know, we're diving deep into machine learning and artificial intelligence, and we looked at OpenCV or CV2 to do a facial detection project. And now what we want to do is we would like to take a look at TensorFlow, which is definitely a very powerful tool, and that's sort of what's next. So let's go ahead and get started with the presentation. Without further ado, this is the Computer Programming University. Let's begin.
Click subscribe, then click the bell. Click the bell because you don't want to miss out on more awesome content that I'll be posting soon right here on this channel.
That's right. You definitely don't want to miss out. All right, let's go ahead and get started. Let's pull up our TV and hit play.
Alrighty, shall we get started? So thanks everybody for coming to this session. I'm going to be talking about TensorFlow, and particularly TensorFlow from a programmer's perspective, so machine learning for programmers. I'd like to show some code samples of using TensorFlow in some simple scenarios, as well as one slightly more advanced scenario. But before I do that, I always like to just do a little bit of a level set. And if you were at the previous session, sorry, some of the content's going to be similar to what you've seen already. But when I like to think about AI, and when I come to conferences like this one about AI, or if I read the news about AI, there's always stories about what it can do or what it might do, but there's not a whole lot about what it actually is. So part of my mandate and part of what I actually like to educate people around is from a programmer's perspective, what AI actually is, what it is for you, what you can begin to learn how to program, and then how you can apply it to your business scenarios. But we're also at the cusp of like this revolution in this technology, and lots of people are calling it like the fourth industrial revolution. And for me, I can only describe it as like it's the third big shift in my own personal career. And so for me, the first one came in the early to mid 90s when the web came about. And if you remember, when the web came about, we were all desktop programmers. I personally, my first job was I was a Visual Basic programmer programming Windows applications. Anybody ever do that? It was fun, wasn't it? And so then the web came around, and what happened with the web then is it changed the audience of your application from one person at a time to many people at a time. You had to start thinking differently about how you built your applications to be able to scale it to lots of people using it, and also the runtime changed. Instead of you being able to write something that had complete control over the machine, you would write something to this sort of a virtual machine that the browser gave you. And then maybe that browser would have plugins like Java and stuff like that you could use to make it more intelligent. But as a result, what ended up happening was this paradigm shift gave birth to whole new industries. And I worked for a small company called Google. Anybody heard of them? And so like, you know, things like Google weren't possible. Anybody remember Gophers? Yeah, so that's really old school, right? So what Gophers were almost the opposite of a search engine.
Wow.
Search engine, like, you know, you type something into it and it has already found the results and it gives them to you. A Gopher was this little application that you would send out into the nascent internet, and it would crawl everywhere, a little bit like a spider, and then come back with results for you. So
I remember that. Those are the good old days. That's, for me, talking 1992, 1993. It was Gopher and Archie, if I remember correctly. And it was all black and white. White text on a black and white background, no GUI. Yeah. Fun times.
So for me, like, you know, whoever had the great idea to say, let's flip the axes on that, you know, and come up with this new business paradigm, ended up building the first search engines. And as a result, companies like Google and Yahoo were born. Ditto with things like Facebook. You know, that wouldn't have been possible with the browser. Can you imagine trying to, before pre-internet, where there was no standard protocol for communication, you know, and you'd write desktop applications, can you imagine being able to build something like a Facebook or a Twitter? It just wasn't possible. So that became, to me, the web was this first great tectonic shift in my own personal career. The second one then came with the advent of the smartphone. So now users had this device that they can put in their pocket that's got lots of computational power, it's got memory, it's got storage, and it's loaded with sensors like cameras and GPS, etc. Now, think about the types of applications that you could build with that. Now it's a case of companies like Uber became possible. Now, I personally believe, by the way, that all of the applications are built by introverts, because like you'll see all of these great things that you can do nowadays, it's because they serve introverts. I'm highly introverted, and one thing I hate to do is stand on a street corner and hail a taxi. So when Uber came along...
What's up, Survival of the Fittest? Good to see you, man. Taking a deeper dive into machine learning today. Formal presentation. This should be interesting. This guy's pretty good, so I'm interested to see what he's going to show us today. He's going to show us some of the code. He's going to talk about also some of the potential of what can be done with the technology. So pretty wide audience for what he's presenting here.
Along, it was like a dream come true for me that I could just do something on my phone and a car would show up. And now with shopping, it's the same kind of thing, right? I personally really dislike going to a store and having somebody say, can I help you? Can I do something for you? Can I help you find something? I'm introverted. I want to go find it myself, put my eyes down, take it to the cash register, and pay for it. And now online shopping, it's like, it's done the same thing. So I don't know why I went down that rabbit hole, but it's it's just one that I find is like the second tectonic shift has been that, like the advent of the mobile application, so that these new businesses, these new companies became possible. So the third one that I'm seeing now is the AI and the machine learning revolution. Now, there's so much hype around this, so I kind of like to draw the diagram of the hype cycle. And so if you think about the hype cycle, every hype cycle starts off with some kind of technological trigger. Now, with AI and machine learning, that technological trigger really happened a long time ago. Machine learning has been something, and AI has been something that's been in universities. It's been in industry for quite some time, decades. So it's only relatively recently that the intersection of compute power and data has made it possible so that now everybody can jump on board, not just university researchers. And with the power of things such as TensorFlow that I'm going to show later, anybody with a laptop can start building neural networks, where in the past neural networks were reserved for like the very best of universities. So like that technological trigger that's like rebooted in many ways the AI infrastructure has only happened in the last few years. And with any hype cycle, what happens is you end up with this peak of increased expectations where everybody's thinking AI is going to be the be-all and end-all and will change the world and will change everything as we know it, before it falls into the trough of disillusionment, and then at some point we get enlightenment and then we head up into the productivity. So when you think about the web, when you think about mobile phones and those revolutions that I spoke about, they all went through this cycle, and AI kind of went through this cycle. Now, you can ask 100 people where we are on this life cycle right now, and you'll probably get 100 different answers, but I'm going to give my answer. I think we're right about here. And when we start looking at the news cycle, it kind of shows that. We start looking at news, we start looking at glossy marketing videos, AI is going to do this, AI is going to do that. At the end of the day, AI isn't really doing any of that. It's smart people building neural networks with a new metaphor for programming have been the ones who've been able to do that and have been able to build out these new scenarios. So we're still heading up that curve of increased expectations, and at some point we're probably going to end up in the trough of disillusionment before things will get real. And things, you'll be able to really build whatever the Uber or the Google of the AI generation is going to be. It may be somebody in this room will do that, I don't know. So at Google, we have this graph that we draw that we try to use that we train our internal engineers and our internal folks around AI and around the hype about AI. And we say, like, we kind of like to layer it in these three ways. First of all, AI, from a high level, is the ability to program a computer to act like an intelligent human. And how do you do that? There might be some traditional coding in that, but there may also be something called machine learning in that. And what machine learning is all about is, instead of writing code where it's all about how the human solves a problem, how they think about a problem and expressing that in a language called like Java or C# or C++, it's a case of you train a computer by getting it to recognize patterns and then open up whole new scenarios in that way. I'm going to talk about that in a little bit more. Then another part of that is deep learning, with the idea behind deep learning is now machines being able to take over some of the role that humans are taking in the machine learning phase, where the idea is that where machine learning is all about, I'm going to, for example, I'm going to show a slide next about activity detection. But in case of activity detection, instead of me explicitly programming a computer to detect activities, I will train a computer based on people doing those activities. So let me think about it. Let me describe it this way. First of all, how many people in this room are coders? You've written code. Oh, wow, most of you. OK, cool. What languages, out of interest? Just shout them out. C#, thank you. Python. OK, I've written a bunch of books on C#. I still love it. You know, I don't get to use it anymore, but it's nice to hear something. So I heard C#, I heard Python.
Python!
C++, OK, cool.
Yeah!
Now, what do all of these languages have in common? Ruby, nice. What do all these languages have in common? That you as a developer have to figure out how to express a problem in that language, right? So if you think about if you're building a problem, if you're building an application for activity detection, and say you want to detect an activity of somebody walking. Like I'm wearing a smartwatch right now. I love it because since I started wearing smartwatches, I became much more conscious of my own fitness. And I think about how this smartwatch monitors my activity, that when I start running, I want it to know that I'm running, so it logs that I'm running. When I start walking, I want it to do the same thing and count calories and all that kind of stuff. But if you think about it from a coding perspective, how would you build a smartwatch like this one if you were a coder? Now, you might, for example, be able to detect the speed that the person's moving at, and you'd write a little bit of code like this, right? You know, if speed is less than 4, then the person's walking. That's kind of naive, because if you're walking uphill, you're probably going slower. If you're walking downhill, you're going faster. But I'll just keep it simple like that. So in code, you have a problem, and you have to express the problem in a way that the computer understands that you can compile, and then you build an application out of it. So now I say, OK, what if I'm running? If I'm running, well, I can probably go by the speed again, and I say, hey, if my speed is less than a certain amount, I'm walking, otherwise I'm running. I go, OK, now I've built an activity detector, and it detects if I'm walking or if I'm running. Pretty cool, pretty easy to do with code. So I go, OK, now my next scenario is biking. And I go, OK, if I'm going based on the speed, the data of my speed, I can do a similar thing, right? If I say if my speed is less than this much, I'm walking, otherwise I'm running, otherwise I'm biking. So great, I've now written an activity detector, a very naive activity detector, just by looking at the speed that the person's moving at. But now, like, my boss loves to play golf, and he's like, this is great, I want you to detect golf, and tell me when I'm playing golf, and calculate what I'm doing when I'm playing golf. How do I do that? You know, I'm in what I call, as a programmer, I call the oh crap phase, because now I realize that all of this code that I've written, and all this code that I'm maintaining, I now have to throw away, because it can't be used in something like this. This scenario just doesn't become possible with the code that I've written. So when I think about, you know, going back to the revolutions that I spoke about, like, for example, something like an Uber wouldn't have been possible before the mobile phone. Something like a Google wouldn't have been possible before the web. And something like my golf detector, it wouldn't be possible, or it would be extremely difficult, you know, without machine learning. So what is machine learning? So traditional programming, I like to summarize in a diagram like this one. And traditional programming is a case of you express rules using a programming language like Ruby or C# or whatever. And you have data that you feed into it, and you compile that into something that gives you answers. So keeping the very simple example that I have of an activity detector, that's giving me the answer of you're playing golf, you're running, you're walking, all those kind of things. The machine learning revolution just flips the axes on this. So the idea behind the machine learning revolution is now I feed in answers, I feed in data, and I get out rules. So instead of me needing to have the intelligence to define the rules for something, this revolution is saying that, OK, I'm going to tell a computer that I'm doing this, I'm doing that, I'm doing the other, and it's going to figure out the rules. It's going to match those patterns and figure out the rules for me. So now something like my activity detector for golf and walking and running changes. So now, instead of me writing the code for that, I would say, OK, I'm going to get lots of people to walk. I'm going to get lots of people to wear whatever sensor it is, like maybe it's a watch or a smartphone in their pocket. And I'm going to gather all that data, and I'm going to tell a computer, this is what walking looks like. I'm going to do the same for running. I'm going to do the same for biking. And I may as well do the same for golfing. So now my scenario becomes expandable, and I can start detecting things that I previously would not have been able to detect. So I've opened up new scenarios that I previously would not be able to program by using if-then rules or using whatever language, C. Anybody remember the language Prolog?
Nope.
Anybody use that? Yeah. You know, even Prolog couldn't handle that, even though they said Prolog was an AI language. So
I remember Pascal.
The idea behind this is it kind of emulates how the human mind works. So instead of like me telling the computer by having the intelligence to know what golf looks like, I train the computer by taking data about what golf looks like, and the computer recognizes that data, matches that data. So in the future, when I give it more data, it will say, that kind of looks like golf, so I'm going to say this is golf. So we talk about learning. We talk about the human brain. So I always like to think, like, well, think about how you learn something. Like maybe this game. Anybody remember this game? Everybody knows how to play tic-tac-toe. I gave a talk similar to this in Japan earlier this year, and they had this really strange name that I couldn't remember for it. But this is a very simple game, right? Now, if I were to ask you to play that game right now, and it's your move, where would you go? How many people would go in the center? Okay, how many people would not go in the center? We need to talk. You know, so like you probably learned this as a young child, and maybe you teach this to children. But the strategy of winning this game, if it's your turn, you will never win this game unless you're playing against somebody who doesn't know how to play the game by not going in the center first. Now remember how you learned that. Okay, if you have a really tough teacher like me, I would teach my kids by beating them every time at the game. And you know, that kind of stuff. So if they would start in the corner, I would beat them, and they would start somewhere else, and I would beat them at the game. And you know, keep doing these kind of things until they eventually figured out that they have to go in the center or they're going to lose. Right? So, you know, that was a case of, this is how the human brain learns. So how do we teach a computer the same way? Now think about, like, for example, if your kids goes in, they've never seen this board before. So, you know, in this society, we read left to right, top to bottom. So the first thing they'd probably do is go in the top left-hand corner. And then you'd go in the center, and then they'd go somewhere else, and you go somewhere else, and then they go somewhere else, and you get 3 in a row, and you beat them. They now have what, in machine language parlance, is a labeled example. They see the board, they remember what they did on the board, and that's been labeled as they lost. You know, then they might play a game, and they have another labeled example of they lost. And they'll keep doing that until they have labeled examples of tying, and then maybe eventually labeled examples of winning. So knowing how to learn is a step towards this kind of intelligence. And this is when we talk about machine learning, when we get our data and we label them, it's exactly the same as teaching a child how to play tic-tac-toe or noughts and crosses. So let's take a look at, so if I go back to this diagram for a moment before I look at some code, now the idea is like thinking in terms of tic-tac-toe. You have the answers of experience of playing the game, you have the labels for that, you know, that you won, you lost, whatever, and out of that, as a human, you begin to infer the rules. Did anybody ever teach you, you must go first? If you do, you must go in the center first. If you don't go in the center first, you go in a corner. If you don't go in a corner, you block somebody with 2 in a row. You know, you don't learn by those if-then rules. I know I didn't, and most people I speak to didn't. As a result, they ended up playing the game and they infer the rules for themselves. And it's exactly the same thing with machine learning. So you build something, the computer learns how to infer the rules with a neural network, and then at runtime you give it data and it will give you back classifications or predictions or you know, give you back intelligent answers based on the data that you've given it. So let's look at some code. So this is what we call the training phase, this is what we call the inference phase. But like enough theory, so I like to explain a lot of this in coding. So a very simple hello world scenario, as all programmers have, is I'm going to use some numbers. And I'm going to give you some numbers. And there's exactly the same as teaching a child. And you know, that can be something. Like maybe this game. Anybody remember this game? Everybody knows how to play this game, right? It seems, by the way, this game has different names in every country, and it's always hard to remember. Like, I grew up calling it noughts and crosses. Ed's nodding. Most people grew up maybe calling in this country tic-tac-toe. I gave a talk similar to this in Japan earlier right now, and it's your move. Where would you go? How many people would go in the center? Okay, how many people would not go in the center? We need to talk. You know, so like you probably learned this as a young child, and maybe you teach this to children. But the strategy of winning this game, if it's your turn, you will never win this game unless you're playing against somebody who doesn't know how to play the game by not going in the center first. Now remember how you learned that. Okay, if you have a really tough teacher like me, I would teach my kids by beating them every time at the game. And you know, that kind of stuff. So if they would start in the corner, I would beat them, and they would start somewhere else, and I would beat them at the game. And you know, keep doing these kind of things until they eventually figured out that they have to go in the center or they're going to lose. Right? So, you know, that was a case of, this is how the human brain learns. So how do we teach a computer the same way? Now think about, like, for example, if your kids goes in, they've never seen this board before. So, you know, in this society, we read left to right, top to bottom. So the first thing they'd probably do is go in the top left-hand corner. And then you'd go in the center, and then they'd go somewhere else, and you'd go somewhere else, and then they'd go somewhere else, and you get 3 in a row, and you'd beat them. They now have what, in machine language parlance, is a labeled example. They see the board, they remember what they did on the board, and that's been labeled as they lost. You know, then they might play a game, and they have another labeled example of they lost. And they'll keep doing that until they have labeled examples of tying, and then maybe eventually labeled examples of winning. So knowing how to learn is a step towards this kind of intelligence. And this is when we talk about machine learning, when we get our data and we label them, it's exactly the same as teaching a child how to play tic-tac-toe or noughts and crosses. So let's take a look at, so if I go back to this diagram for a moment before I look at some code, now the idea is like thinking in terms of tic-tac-toe. You have the answers of experience of playing the game, you have the labels for that, you know, that you won, you lost, whatever, and out of that, as a human, you begin to infer the rules. Did anybody ever teach you, you must go first? If you do, you must go in the center first. If you don't go in the center first, you go in a corner. If you don't go in a corner, you block somebody with 2 in a row. You know, you don't learn by those if-then rules. I know I didn't, and most people I speak to didn't. As a result, they ended up playing the game and they infer the rules for themselves. And it's exactly the same thing with machine learning. So you build something, the computer learns how to infer the rules with a neural network, and then at runtime you give it data and it will give you back classifications or predictions or you know, give you back intelligent answers based on the data that you've given it. So let's look at some code. So this is what we call the training phase, this is what we call the inference phase. But like enough theory, so I like to explain a lot of this in coding. So a very simple hello world scenario, as all programmers have, is I'm going to use some numbers, and I'm going to give you some numbers, and there's a relationship between these numbers. And let's see who can figure out what the relationship is. Are you ready? Okay, here's the numbers. So where x is -1, y is -3, where x is 0, y is -1, etc., etc. Can you see the relationship between the x and the y?
Nope.
So if y equals something, what would y equal? 2x minus 1. Excellent. So the relationship here is y equals 2x minus 1. How do you know that? How did you get that? What's that? I can't hear you, sorry. Oh, linear fit. Okay, thanks. Yeah, so, you know, you've probably done some basic geometry in school, and you think about, you know, usually there's a relationship y equals mx plus c, something along those lines. So you start plugging an m and a c in your mind until you find something that works, right? So you go, okay, well, if y is -3, maybe that's a couple of x's, which will give me -2, and I'll subtract 1 from that, give me -3. And then I'll try that with 0 and 1. Yep, that works. And I'll try that with 1 and 1. That works. So what happened is there were a couple of parameters around the y that you started guessing what those parameters were and started trying to fit them in to get that relationship. That's exactly what a neural network does. And that's exactly the process of training a neural network. When you train a neural network to try and pick a relationship between numbers like this, all it's doing is guessing those random parameters, calculating, look through each of the parameters, calculate which ones it got right, which ones it got wrong, calculate how far it got them wrong by, and then try and come up with new values that will be closer to getting more of them right. And that's the process called training. So whenever you see training and talking about needing lots of cycles for training, needing lots of GPU time for training, all the computer is doing is trying, failing, trying, failing, trying, failing, but each time getting a little closer to the answer. So let's look at the code for that. So using TensorFlow and using Keras, I don't have the code on my laptop, so I got to look back at the screen, sorry. So using TensorFlow and Keras, here's how I'm going to define a neural network to do that linear fitting in just a few lines. So the first thing I'm going to do is I'm going to create my neural network. This is the simplest possible neural network. It's got one layer with one neuron in it, and this is the code to do that. So where you see keras.layers.dense, units equals 1, input shape equals 1, that's all that I'm doing is I'm saying I'm at a single neuron, I'm going to pass a single number into that, and you're going to try and figure out what the number I want to come out of that is. So very, very simple. So then my next line of code is, remember I said, like, what a neural network is going to do is try and guess the parameters that will make all the numbers fit. So it will come up with a couple of rough guesses for these parameters, and then it has these two functions. One's called a loss function, and one's called an optimizer. And all they're doing is, like, if you remember that set of 6 numbers I gave you, it's like saying, okay, well, if y equals something times x plus something, I'm going to guess those 2 somethings. I'm going to measure how many of my y's I got right. I'm going to measure how far I'm wrong in all of the ones that I got wrong. And then I'm going to try and guess new values for those somethings. So the loss function is the part where it's measuring how far I got wrong. And the optimizer is saying, okay, here's what I got the last time. I'm going to try to guess these new parameters until I'll keep going until I get y equals 2x minus 1, or something along those lines. So that's all you do. You just compile your model, you specify the loss function, you specify the optimizer. These are both really heavy mathy kind of things. One of the nice things about Keras, one of the nice things about TensorFlow is they're all done for you. You're just going to specify them in code. And so I'm going to say, I'm going to try the mean squared error as my loss function, and I'm going to try something called SGD, which is stochastic gradient descent, as my optimizer. And every time it loops around, it's going to just guess new parameters based on those. OK, so then the next thing I'm going to do is I've got to feed my values into my neural network, right? So I'm going to say my x's is going to be this array, -1, 0, 1, etc. My y's are going to be this array. So here I'm creating the data. And so I just get them, and I load them into a couple of arrays. This is Python code, by the way. And now, all that I'm going to ask my neural network to do is to try and come up with an answer. And I do that with the fit method. So here I just say, hey, try and fit my x's to my y's. And this epochs equals 500 means you're going to just try 500 times. So it's going to loop 500 times like that. Remember I was saying it's going to guess those parameters. It's going to get it wrong. It's going to optimize. It's going to guess again. It's going to get it wrong. It's going to optimize. So in this case in my code, I'm just saying, do that 500 times. And at the end of those 500 times, it's going to come up with a model that if I give it if I give it an x, it's going to give me what it thinks the y is for that x. Okay, and you do that using model.predict. So if I pass it model.predict for the value 10, what do you think it would give me? If you remember the numbers from earlier, y is 2x minus 1, what do you think it would give? 19, right? It doesn't. Because it'll give me something really close to 19. It gives me about 18.97, and I'm going to try to run the code in a moment to show. But why do you think it would do that? What's that?
It's predicting.
It's predicting, and it's just being trained on a very few pieces of data, right? With those 6 pieces of data, it looks like a line and it looks like a linear relationship, but it might not be. Right? There's room for error there. That, with the fact that I'm training on very, very little data, this could be a small part of a line, for all we know, goes like this, instead of being linear once you move out of those points. And as a result, those kind of things get factored into the model as the model's training on it. So you'll see it's going to get a very close answer, but it's not going to be an exact answer. Let me see if I can get the code running. It's a little complex with this laptop, so when I'm presenting, it's hard to move stuff over to that screen. Just 1 second. This requires some mouse foo. All right, so I have that code. Let's see. Yeah. So you can see that code I have now running up there. And if you look right at the bottom of the screen over here, we can see here's where it has actually done the training. It's done 500 epochs worth of training. And then when I called the model.predict, it gave me this answer, which is 18.976414. And that was one that I ran earlier. I'm just going to try and run it again now, if I can. But it's really hard to see. So I'll click that run arrow. So this IDE is PyCharm, by the way. So you see it ran very quickly because it's a very simple neural network. And as a result, I was able to train it through 500 epochs in whatever that is, half a second. What did it give me this time? Was 18.9747? Is that what I see? So again, very simple neural network, very simple code. But this kind of just shows some of the basics for how it works. So next I want to just get to a slightly more advanced example once I get my slides back. Whoops. Okay. So that was very simple. That was Hello World, right? We all remember our first Hello World program, which we wrote. If you wrote it in Java, it was like 10 lines. If you wrote it in C#, it was 5 lines. If you wrote it in Python, it was 1 line. If you wrote it in C++, it was like 300 lines. Do you remember that? I remember Petzold's book on programming Windows. Anybody ever read that? The whole first chapter was how to do Hello World in MFC, and it was like 15 pages long. I thought it was great. So, you know, but that was a pretty easy example. That to me is the Hello World of machine learning, just doing that basic linear fitting. But let's think about something more complicated. So here are some items of clothing. Now, as a human, you're looking at these items of clothing and you've instantly classified them and you instantly recognize them, or at least hopefully most of them. But think about the difficulty for a computer to classify them. For example, there are two shoes on this slide. Right, one is the high heel shoe in the upper right, and one is the sneaker in the second row. But they look really different to each other, right? Other than the fact that they're both red, you know, and you think they vaguely fit a foot. The high heel, obviously, your foot has to change to fit it, and the sneaker, you know, the foot is flat. But as a human brain, we automatically recognize these and we see these as shoes. Or if we look at the two shirts in the image, right? One of them doesn't have arms because we automatically see it as being folded, the one with the tie. And then the green one on the lower left, we already know it's a shirt, it's a t-shirt, because we recognize it as such. But think about how would you program a computer to recognize these things given the differences? It's really hard to tell the difference between a high-heeled shoe and a sneaker, for example. So the idea behind this is there's actually a data set called Fashion MNIST. And what it does is it gets 70,000 items of clothing, and it's labeled those 70,000 items of clothing in 10 different classes, from shirts to shoes to handbags and all that kind of thing. And it's built into Keras. So one of the really neat things that came out of the research behind this, by the way, is that the images are only 28 by 28 pixels. So if you think about it, it's faster to train a computer if you're using less data. You saw how quickly I trained with my linear example earlier on. But if I were to try and train it with like high definition images of handbags and that kind of stuff, it would still work, but it would just be slower. And a lot of the research that's gone into this data set, they've actually been able to train it and show how to train a neural network that all you need is a 28 by 28 pixel image for you to be able to tell the difference between different items of clothing. As you're doing probably right now, you can take a look and you can see which ones are pants, which ones are shoes, which ones are handbags, that kind of thing. So this allows us to build a model that's very, very quick to train. And if I take a look, here's an example of one item of clothing in 28 by 28 pixels. And you automatically recognize that, right? It's a boot or shoe or something along those lines. And so this is the kind of resolution of data that all you need to be able to build an accurate classifier. So let's look at the code for that. So if you remember earlier on, the code that I was building was I created the neural network, I compiled the neural network by specifying the loss function and the optimizer, and then I fit it. So in this case, a little bit more complex. Your code's going to look like you're going to use TensorFlow. From TensorFlow, you're going to import the Keras namespace, because the Keras namespace really nicely gives you access to that Fashion MNIST data set. So think about all the code that you typically have to write to download those 70,000 images, download their labels, correspond a label with an image, load all of that in, that kind of stuff. All that coding is saved and just put into these 2 lines of code. And so one of the neat things also about Python that I find that makes Python great for machine learning, because that second line of code there where it's like bracket train images, comma train labels, comma bracket test images, test labels equals Fashion MNIST load data. What that's actually doing is it's loading data from the data set, which is stored in the cloud. It's sorting that 70,000 items of data into 4 sets. Those 4 sets are then split into 2 sets, one for training and one for testing. And that data is going to contain, the one on the left there, the training images, is 60,000 images, and 16 images created the neural network, train it and show how to train it. It would still work, this, by the way. It's a shirt, it's a t-shirt, because we recognize it. And then recognize it. A computer builds those 70,000 items. 70,000 items. The idea behind this is and a sneaker, for example. So the idea behind this is there's actually a data set called Fashion MNIST. And what it does is it gets 70,000 items of clothing, and it's labeled those 70,000 items of clothing in 10 different classes, from shirts to shoes to handbags and all that kind of thing. And it's built into Keras. So one of the really neat things that came out of the research behind this, by the way, is that specifying the loss function and I created. So let's look at the code for that. So if you remember earlier on, the code that I was building was I created the neural network, I compiled the neural network by specifying the loss function and the optimizer, and then I fit it. So in this case, a little bit more complex. Your code's going to look like you're going to use TensorFlow. From TensorFlow, you're going to import the Keras namespace, because the Keras namespace really nicely gives you access to that Fashion MNIST data set. So think about all the code that you typically have to write to download those 70,000 images, download their labels, correspond a label with an image, load all of that in, that kind of stuff. All that coding is saved and just put into these 2 lines of code. And so one of the neat things also about Python that I find that makes Python great for machine learning, because that second line of code there where it's like bracket train images, comma train labels, comma bracket test images, test labels, equals fashion mnist load data. What that's actually doing is it's loading data from the data set, which is stored in the cloud. It's sorting that 70,000 items of data into 4 sets. Those 4 sets are then split into 2 sets, one for training and one for testing. And that data is going to contain, the one on the left there, the training images, is 60,000 images and 60,000 labels. And then the other set is 10,000 images and 10,000 labels that you're going to use for testing. Now, anybody guess, why would you separate them like this? Why would you have a different set for testing that you would have for training? The clue's in the name, right? So how do you know your neural network is going to work unless you've got something to test it against? You know, earlier we could test with our linear thing by saying by feeding 10 in, because I know I'm expecting 2x minus 1 to give me 19. But now it's a case of it'd be great for me to be able to test it against something that's known, that's against something that's labeled, so I can measure the accuracy as I go forward. So that's all I got to do in code. So now if I come back here, let's look at how we actually define the neural network. Oh, sorry, before I do that. So the training images are things like the boot that I showed you earlier on. It's 28 by 28 pixels. The labels are actually just going to be numbers rather than like a word like shoe. Why do you think that would be? So you can define your own labels, and you're not limited to English, right? So for example, 9 in English could be an ankle boot. The second one is in Chinese. The third one is in Japanese. The fourth language, can anybody guess? Bro-gruitine. That's actually Irish Gaelic. Sorry, I'm biased. I have to put some in. You know? So for now, for example, I could build a classifier not just to give me items of clothing, but to do it in different languages. So that's just what my labels are going to look like. So now let's take a look at the code for defining my neural network. So here is, if you remember the first line of code where I defined the single layer with a single neuron for the classification, this is what it's going to look like. And this is all it takes to build this clothing classifier. So you see there are 3 layers here. The first layer, where it says keras.layers.flatten, input shape equals 28 by 28. All that is I'm defining a layer to take in 28 squared values. Remember, the image is a square of 28 by 28 pixels, but you don't feed a neural network with a square. You feed it with a flat layer of values. In this case, the values are between 0 and 256. So I'm just flattening that out, and I'm saying, that's my first layer. You're going to take in whatever 28 squared is. My second layer now is just 128 neurons, and there's an activation function on them, which I'll explain in a moment. And then my third layer is going to be 10 neurons. Why do you think there are 10 in that one? Can anybody guess? So 28 squared for the input, 10 for the output. Anybody remember where the number 10 was mentioned? Yeah, number labels. There are 10 different classes. So what happens when a neural network, when you train it like this one, it's not just going to pop out and give you an answer and say, this is number 3 or this is number 4. Typically what will happen is that you want to have 10 outputs for your 10 different labels, and each output is going to give you a probability that it is that label. So for example, the boot that I showed earlier on was labeled number 9. So neuron 0 is going to give me a very low number. Neuron 1 is going to give me a very low number. Neuron 2 is going to give me a very low number. Neuron 9 is going to give me a very high number. And then by looking at the outputs across all of these neurons, I can now determine which one the neural network thinks it's classified for. Remember, we're training this with a bunch of data. So I'm giving it a whole bunch of data to say, this is what a number 9 looks like, this is what a number 4 looks like, this is what a number 3 looks like. By saying, OK, this is what they are, I encode the data in the same way, and as a result, we'll get our output like this. Now, every neuron has what's called an activation function, and the idea behind that, it's a very mathy kind of thing, but if, in programmers' terms, the tf.nn.relu that you see there, if you think about this in terms of encode, if I say, if x is greater than 0, return x, else return 0. Okay? Very simple function, and that's what the ReLU is. And all that's going to do is, as the code is being filtered in, and then down into those neurons, all of the stuff that's negative just gets filtered out. So as a result, it makes it much quicker for you to train your neural network by getting rid of things that are negative, than getting rid of things that you don't need. So every time when you specify a layer in a neural network, there's usually an activation function like that. ReLU is one of the most common ones that you'll see, particularly for classification things like this. But again, ReLU is a very mathy thing. A lot of times you go to the documentation, you'll wonder what ReLU is, you go look it up, you'll see a page full of Greek letters. I don't understand that stuff. So for me, something like ReLU, like it's as simple as if x is greater than 0, return x, else return 0. All right, so now I've defined my neural network, and the next thing I'm going to do, you'll see the same code as we saw earlier on, where what I'm going to do is compile my neural network. And in compiling my neural network, I got to specify the loss, and I got to specify the optimizer. Now, there's a whole bunch of different types of loss functions. There's a whole bunch of different types of optimizer functions. You know, when you read academic research papers around AI, a lot of them specialize on these to say, for this type of problem, you should use a loss function of sparse categorical cross-entropy because X. You know, for this type of problem, you should use an optimizer, which is an atom-based optimizer, because X. You know, a lot of this, as a programmer, you just have to learn through trial and error. You know, I could specify the same loss function and the same optimizer that I use for my linear, and then try and train my neural network, see how accurate it is, see how quick it is, and then I could try these ones, see how accurate it is, see how quick it is. There's a lot of trial and error in that way. And understanding which ones to use right now is an inexact science. It's a lot like, for example, as a traditional coder, which is better, using a for loop or a do loop, right? Which is better, using a while or using a when? You know, those type of things. And as a result, you see, as you're building your neural networks, there's a lot of trial and error that you'll do here, but reading academic papers can certainly help if you can understand them. So in this case now, like for the fashion MNIST, you know, after a bit of trial and error, we ended up selecting for the tutorial to use these two functions. But as you read through the documentation, you'll see all the functions that are available. So in this case, I'm training it with an atom optimizer. And remember, the process of training, every iteration, it will make a guess. It says, OK, this piece of data, I think it's a shoe. OK, it's not a shoe, it's a dress. Why did I get it wrong? You know, I'll use my loss function to calculate where I got it wrong, and then I'll use my optimizer to change my weights on the next loop to try and see if I can get it better. This is what the neural network is thinking. This is how it works as you're actually training it. So in this case, the atom optimizer is what it's using to do that optimization. The categorical cross-entropy is what it's using for the loss. So now if I train it, it's the same thing that we saw earlier on, model.fit. So all I'm going to say is like, you know, hey, model.fit, I'm going to train it with the input images and the input labels, and I'm just, in this case, I'm going to train it for 5 epochs. Okay, so that epochs number, it's up to you to tweak it. What you'll do is you're training your network, and as you're testing your network, you'll see how accurate it is. Sometimes you can get the process called converging, means as it gets more and more accurate. Sometimes you'll find convergence in only a few epochs. Sometimes you'll need hundreds of epochs. Of course, the bigger and more complex the data set and the more labels that you have, the longer it takes to actually train and converge. But the fashion MNIST data set will actually, using the neural network that I defined on the previous slide, 5 epochs is actually pretty accurate. It gets there pretty quickly with just 5. Okay, and now if I then, you know, I want to test it, and the model itself, if again, the important object here is the model object. So if I call model.evaluate and I pass it the test images and the test labels, it will then iterate through the 10,000 test images and test labels. It will calculate, it will say, I think it's going to be this. It will compare it with the label. If it gets it right, it improves its score. If it gets it wrong, it decreases its score, and it gives you that score back. So the idea here is, remember earlier, when we separate the data into 60,000 for training and 10,000 for test, instead of you manually writing all that code to do all that, you can just call the evaluate function on the model, pass it the test stuff, and it will give you back the results. It will do all that looping and checking for you. Alrighty. So, and then of course, if I want to predict an image, if I have my own images and I formatted them into 28 by 28 grayscale and I put them into a set, now I can just say model.predict my images and it'll give me back a set of predictions. Now what do those predictions look like? So for every image, because the output of the neural network was, there were 10 layers, so every image is going to give you back a set of 10 numbers. And those 10 numbers, as I mentioned earlier on, 9 of them should be very close to 0, and 1 of them should be very close to 1. And then using the one that's very close to 1, you could determine your prediction to be whatever that item of clothing is. So if I demo this and show it in code, let's see, go back here. It's really hard to see it, so forgive me. Oops. I'm going to select fashion. I really need a mouse. I'm going to select fashion. Okay, can you see the fashion code, or is it still showing the linear code? Is that fashion right there? All right. Okay. Did I just close it? I'm sorry, it's really hard to see, so let me go back. Is that one fashion? Up one? All right, that one. Okay. So here's the code that I was showing on the earlier slide. So this is exactly the same code that was on my slides. I'm just going to go down. There's one thing I've done here that I didn't show on the slides, and that was the images themselves were grayscales. So every pixel was between 0 and 256. For training my neural network, it was just easier for me to normalize that data. So instead of it being from 0 to 255, it's a value from 0 to 1, which is relative to that value. And that's what those two lines of codes there. And that's one of the things that makes Python really useful for this kind of thing. Because I can just say, that train images set is a set of 60,000 28 by 28 images. And I can just say, divide that by 255, and that normalizes it for me. So that's why one of the things that makes Python really handy in data science. So but you can see it's just the same code. So I'm going to do a bit of live audience participation. Hopefully I can get it to work with this. So remember I said there are 10,000 testing images. Okay, so somebody give me a number between 0 and 99.99. Don't be shy. What's that? Just 27. Okay. So hopefully I can see it so I can get it. That's not 27, is it? Okay, 27. And here, 27. I tested it earlier with value 4560. So what's going to happen here is that I'm going to train the neural network to identify those pieces of clothing. And so to be able to identify pieces of clothing. I have no idea what piece of clothing number 27 is in the test set. But what it's going to do once it's done is by the end, you'll see it says print the test labels for 27. So whatever item of clothing 27 is, there's a pre-assigned label for that. It'll print that out. And then the next thing it'll do is it'll print out what the predicted label will be. And hopefully the two of them are going to be the same. There's about a 90% chance, if I remember right from this one, that they will. So if I run it, it's going to take a little longer than the previous one. So now we can see it's starting to train the network. And because I'm doing it in PyCharm, I can see in my debug window. So you can see the epochs, epoch 2, epoch 3, epoch 4. This accuracy number here is how accurate it is against testing. So it's about 89% correct. And then you see it's actually printed two numbers below, and they're both 0. So that means for item of clothing number 27, that class was 0. And then the predicted for that class was actually also 0. So we got it right. Yay. Anybody want to try one more? Just to prove that. Let's see if we can. What's that? 42. I love it. That's the ultimate answer. But what is the question? Okay, 42. And I'm guessing 42 is probably also item 0, but let's see. Hopefully I haven't broken any of the bracketing. Let me run it again. So because it's running all of the code, it's just going to train the network again. Okay, there's epoch 2, epoch 3. Hello, there we go. So let's remember earlier I said I'm just training it for 5 epochs. That just makes it a little bit quicker. And I'm also seeing, if you look at the convergence, on epoch 1, it was 82% accurate. Oh, we got it wrong for 42. It predicted it would be a 6, but it's actually a 3. So, but the first epoch, you see this accuracy figure, 8245. That means it calculated it was 82% accurate. The second epoch, 86% accurate. The third, 87, all the way down to the fifth, 89. I could probably train it for 500 epochs, but we don't have the time. But then it might be more likely to get number 42 correct. And thanks, Mr. Douglas Adams, that you've actually given me one that doesn't work, so I can come back and test it. Okay, so that's Fashion MNIST and how it works. And so hopefully this was a good introduction to you for really the concept from a programmer's perspective of what machine learning is all about. And I always like to say, like at talks, that if you only take one slide away from this talk, if you've never done machine learning or you want to get into programming machine learning, take this one here. Because this is really what the core of the revolution is all about. And hopefully the code that I showed you, demonstrates that. That machine learning is really all about taking answers and data and feeding them in to get rules out. I didn't write a single line of code there today that says, this is a t-shirt, or this is a jacket, or this is a handbag. This has sleeves. If has sleeves, then is t-shirt. If has heels, then is, shoe. I didn't have to write any of that kind of code. I just trained something on the data using the below thing, the below part of the diagram, feeding in answers, feeding in data, building a model that will then infer the rules about it. So with that, I just want to say thank you very much, and I hope you enjoy the rest of the conference.
Goal setting, as we know it in the modern Western world, is
click the bell. Because you don't want to miss out on more awesome content that I'll be posting soon, right here on this channel. Welcome aboard. Buongiorno. Salut. Bienvenidos. Hasta luego, todos. I'm so excited that you decided to join the team so we can learn together, grow together, and achieve our dreams. Let's do it. See you soon. Grazie. Learning. We gonna do some learn.
I'm telling you.
Right, subscribe, I'm telling you. All right, guys, so that was a awesome presentation on machine learning and a nice little demo. Definitely good things to think about, and it was interesting seeing TensorFlow and how it can be used. Fortunately, a little bit of a deviation from my experience with OpenCV. OpenCV, I didn't really have to deal with any not sure. I need to spend some time and look at it myself, but the impression I got is that this was a little bit more complex. Not significantly so, but the OpenCV stuff seemed to be, to me, more it just seems simpler to me, so I don't know, I'll have to try it out. I was thinking that there was more math involved, but he was just giving a math exercise where he had the numbers and he wanted you to try to figure out what the pattern is. So that was just sort of an example. That wasn't an actual part of the actual programming. However, I don't know, I just get this feeling that I don't know, maybe that threw me off, because again, I'm not good at math, so I was like, oh no, math, and then maybe that colored my whole perception of the entire presentation. I don't know, even the code itself, I don't know, I gotta look at it. I think I'm making something out of nothing. It's my first time seeing it. You know, just like anything else, you need to acclimate. You know, I gotta go in there and write some code and see what it's like. You know, and from that I can determine how complex or not complex it is. But definitely very interesting, and it's perfect for where I'm headed next, because I did the image detection. That was cool. I wanted to do image recognition, which you didn't do, but I guess the main theme of where I'm headed next is I want to deal with training. I didn't do any training previously, so I want to do, yes, there's supervised and unsupervised training. I guess I want to do, I don't even remember. I got a review, but I'm guessing I want to do supervised training. But essentially, I want to do model generation, where I'm gonna actually produce my own training data that I'm going to utilize for the program. So, for example, I could train it to recognize this. Not a good example, because it's just one item. That even makes sense. Like if I were to show it this, and this, and then like a phone or something, and then an air can, then have it, and then tell it this is a horse. No, that doesn't make any sense. I need examples of different examples of the same thing. So I can say this is a book. This is a book. Book. This is not a book. And that should be interesting. But then the thing with that though is in order to have an effective model, you need a lot of data. So it would be very difficult for the program to be able to detect that this is not a book compared to the other items, because they look very similar, and it's just not enough information to work with. I mean, ideally you want to train, I mean, it could be thousands of photos, so thousands of books. So that would mean that I can't really ideally use anything physical for training purposes, because I would need thousands of anything. I don't have thousands of anything. So logically that would mean my models would have to be trained using artificial data. So meaning pictures from online. So I need to get a source of images from online. So maybe that might be something where I could do a web scraping project. I've been wanting to do that. I didn't do anything. Started pulling some stock quotes and stuff like that, but I never really built anything. So I could build something that scrapes Google Images for types of images. I mean, that's the first thing I can think of. So pull images of a certain type from Google Images and use it as training data. Then once I do that, if the images that I've trained it on, which basically I'm building a classifier, if I can test against things I have here. So I could download thousands of book images to train it. Then I could be like, is this a book? And then I could have a reasonable expectation that my program might actually be able to detect whether that's a book or not. So that'll be interesting, because what makes this not a book? Yes, some of the patterns. See, now you got to look at how the machine learning works, right? So what makes this? Because it looks very similar to a book. It's a square, little square object like this. It's shiny, like a book would be. It's got some text on the front. But if we compare this to the books, we can already see there's some patterns. If you look at it from a simplistic approach, I could see, well, how's the computer going to know? But it will know because it has a lot of data which gives it unique book features which don't exist on that. So first book here, we've got not just text, but specific types of text. We have a publisher down here in the bottom. Have something about, I guess, who wrote the book. We have a big title on the front, not on the side like that. And we got more writing. So a lot of writing on this. Now, I'm sure there's some DVD covers that might have more writing than that DVD cover, but they probably don't have a publisher and who wrote the book and all that kind of stuff. So again, a similar pattern. We have a 2-row title, big letters. We have a lot more writing again. We have 130 programs that get things done. Really just a graphic. There's more text here. So one thing to remember is it's looking for patterns. So even though this doesn't have the other writing, it's going to look for what are the trends. So give it thousands of books. What are the trends? The fact that one book doesn't have something that's common doesn't matter. What matters more is the trends. So typically books have what features? And then does the image that you're looking at have those features? Or anything that looks like those features? So once again, here's another Pocket Python. It's got, I guess, the author on the bottom. I guess you guys can barely see that. Sorry. Got the author on the bottom. It's got a 3-row title. Big letters, so big letters on the front. It's got O'Reilly. Now this is the second book that had this thing on the side. So see another pattern, 5th edition. So keep in mind, so if I showed it another book, right, it could see, okay, it's got these letters, this same kind of patterns on the front. It's got the same kind of letters down here as well. And then it would get more points for having this thing on the corner, this black thing, because that's something that it would see perhaps on a lot of different books. I mean, so far we've only seen 2 of those, but I know that that's a common thing. I mean, look, literally, is this the same publisher? Well, that's an O'Reilly thing, perhaps. These are both O'Reilly books. And also O'Reilly. O'Reilly is a book publisher, so it might, through its scanning of the image, it recognizes this letter O'Reilly, the name O'Reilly, and it has tons of records of O'Reilly books. So books that had this text on there. So you showed another O'Reilly book, and it's like, okay, big letters up here, author on the bottom, publisher somewhere, whatever, and then this. That could be the thing where it's like, okay, very high probability that that's a book based on my data, right? Here's another book, Dream Manager. Dream Manager, again, similar pattern. So you got a 2-row title, right? You've got, I guess, the author on the bottom, I believe some kind of subtitle down there. So again, pattern, right? Very similar pattern. Also notice the white border. There's a white line bordering it. That might be something that is common on many books. So, you know, if it has a lot of data about this line border, and you have a book with the line border, you have the titles like that. A better classifier would be one that knows DVDs, Blu-rays, and books, because that'll be even better if it knows what Blu-ray discs look like. So not only can it look for book features to identify the likelihood that it's a book, but also it could know what a Blu-ray disc is, and then see it has the Blu-ray symbol. There's a Blu-ray symbol on the top of this. So it's missing a lot of the book signals, right? It doesn't have the title across the top. It doesn't have the author on the bottom. And then it's got this Blu-ray symbol, which it only knows in Blu-ray discs. So that would make it even easier to be able to distinguish that. So here's another book, final book here. So this book has a 3-row title, the five patterns of extraordinary careers. All right, Guide to Achieving Success and Satisfaction. So it's got more writing on the bottom. All right, and that's essentially how it works. So I need to figure out, I think what I'll do, what I'm gonna do. Build a program that can recognize make up a term now, can recognize the ethnicity. You're not, you have no idea where I'm going with this. Program that can recognize the ethnicity of an automobile. German versus Italian versus Japanese. Pick up on the design aesthetic differences between the nations. So give it a bunch of Italian cars, bunch of German cars. Actually give it a picture and be like, hey, what country made this car? A Mercedes-Benz. Like Russia. give it a Toyota Corolla. Japanese. Okay, that's racist. Anyway, so that's just an idea. And you see, that's the thing. Build something. That's again that killing two birds with one stone in a way. I love cars. So I have a passion for cars. So introducing that into my programming, I think would be an awesome, awesome thing. Because now it's not just something, you know, sort of silly just to build something. It's something where, you know, it'd be fun to actually see it. If it works, have it recognize, you know, hey, that's a German car. Hey, that's a whatever car. That'll be kind of cool. And then to search online for all kinds of different cars to test it out on. I wonder if it's gonna guess this. I wonder if it's gonna guess that. So I think that'd be a fun thing. So I think I'll add that to the list of the many projects that I want to get into. How many will be finished? While it's good to finish projects, especially if you're getting paid for them, you don't have to necessarily finish a project to benefit from it. Start a project and you learn a lot from it. That's still a good thing, whether you finish it or not. Thing with finishing a project, if it's something, obviously if you're getting paid for it, then you need to get it done. If not, the thing with finishing it is there's a skill in terms of time management and discipline that's required to get things done, which you use in a business scenario, like when you're doing a, you know, you get hired or you're doing freelance, whatever it is. So you don't have that ability and you're doing a whole bunch of things and not getting them done. You're not doing yourself any favors. You know that that's an issue, then you need to work on it and figure out whatever you need to figure out to make sure that you can actually bring a project to completion. If that's not an issue, then still not necessarily advisable, but not that big of a deal. You can jump into a project, extract what you need from it in terms of skill set, experience, and take it with you. You don't have to complete something to learn from it. Even going through the process of thinking about how can I build something like this. So much learning can come from just that thought process before you've even written a bit of code. So, there you have it. Anyway, that's my food for thought. And this will be me signing off for today. I know I did a lot of live streams today. We had Igor on this morning. That was awesome. I'm going to try to cut up that interview and post it up. I got another interview coming up as well. And CKKO, going to be doing an interview with him pretty soon, hopefully. So stay tuned. Lots of awesome content coming up right here on this channel. First Last says, maybe just recognize exactly what the car is, like specifically 1995 Honda Civic SV. Yeah, that could be done, but that's a lot of data. I mean, you wanna do a car recognition program. I mean, if you limit, I get, well, okay, let me qualify that. You limit the data set to something, let's say you're just doing Honda cars, so not trucks, for example, then fine. But to try and categorize like every car, I mean, then again, that's the beauty of programming, man. There's different ways to skin a cat. Problem solving. Look at something and you think it's impossible, but if you think long enough, I'm thinking that's a lot of data, and it is. Now I'm thinking this is 2018, the age of the internet. I could literally type in just about any car right now and pull up pictures of it. So there might be a way to do that. I'm not sure offhand, but I think there's a way you could leverage that technology using web scraping. The only thing is you need a little insane though, because I can't pull the images of the cars without actually requesting the cars. So I'd need a list of all these cars, and that's a ton of cars. Well, even with that, I still feel like I would want to limit the scope of the application. So maybe cars from the last 10 years or something like that. Yeah, but that's a serious undertaking, I think. But what if somebody wanted to actually build that, right? So a company is building some product where they want to be able to recognize just a car. How would they do that? So I'm thinking more as just me sitting here and doing it, but as a business, well, let me do a quick check. Let me look for I need a source of cars of every car brands. All car brands list car logos. Well, I got an answer for the logos. There are millions of pictures. Yeah, the pictures are there, but you need the names of the cars. You need context. I can't just download a bunch of pictures. So that's what I'm saying. I would want to start with a list of cars. And then from the list of cars, I could easily get the pictures. If I had a list of cars, Toyota Corolla, Toyota Camry, Toyota whatever, I can take that list, crawl the internet or scrape the internet, Google Images, whatever, for pictures of Toyota Camrys. And then you can do math just to count the years. So you do 91 Corolla, search for 91 Corolla, 92 Corolla, 93 Corolla, 94 Corolla, 95 Corolla, 96 Corolla. You know what I mean? So you can just go every year and download pictures. Now you've got every single Corolla documented. Then you gotta account for some noise in there because you wanted this to be done by the application. So there's gonna be some pictures that are labeled as Toyota Corolla, which don't have Corollas in there. So I would want it. Wow, I would almost think you might want to use machine learning, a machine learning algorithm to generate the actual data, which I haven't heard of that concept. I'm sure it's probably something being used already, but normally you use the algorithm to process the data that you already have. But what about using an algorithm to generate the data and then another algorithm to process the data? The purpose of the first algorithm is essentially to do rejections. So basically, I would write an algorithm that would look, so you pull a bunch of pictures of Toyota Corollas, right? So remember, this is the program doing it. The program doesn't know what a Corolla looks like, right? So, and you're not watching this, it's all automatic. So one of those pictures has like a chicken in there, or has like a bus or something. So the algorithm that I would write would be one that looks for trends and patterns and rejects any images that are greatly deviated from the others. So you would identify these outliers. So, you know, you have a whole bunch of images of a 1993 Toyota Corolla, and they all have certain patterns, but there's this one image that there's just so much different from everything else. The probability that that's actually a Corolla is very low, so reject that image. And that's all that does, basically. Get rid of high probability errors and just remove them. These are negative images. Get them out. So basically do a data cleanup, a data cleanup algorithm that rejects bad images. You run that each car model, each year, bunch of pictures, clean them up. Next year, bunch of pictures, clean them up. Bunch of years, next pictures, clean them up. And then you go to the next car model, do the same thing. Next car model, do the same thing. But even that, so again, I guess I'm getting back to the business perspective. Stop thinking about limitations of me. We would definitely want to leverage some kind of like Amazon cloud, or maybe Google cloud infrastructure, because this is going to take a long time. That's a lot of images. That's a lot of processing. It would take forever to do that. So we want to use one of those services to do it. Yeah, that's my thoughts on that. Oh, there you go. Yep. And that was my thoughts. I wanted to do like Italian cars. So you're saying rare and limited cars. Yeah. That's a short list, right? I look at Lamborghini. I mean, it's not that many. You get the Miura, you got the Diablo, the Countach, the Rebenton, the Murcielago, LP640, the Gallardo, you have the Aventador, you have the what's the other one? The new one now is the Huracan. Now they got the Urus or whatever it is, the SUV thing. You got the Sesto Elemento. And I pretty much named probably 97% of their cars. Can't think what I've forgotten. They had a Jeep truck thing as well. But I mean, what are we talking about? I mean, well, there's different models of each. So I have to account for that. They did like a ton of Gallardos, so maybe I don't know, maybe 24 Gallardos. 2 or 3 dozen Gallardo, but still, it's not that many cars, so it wouldn't take that long to build up the list at all. But that's how I would do it, man. So I think I'm gonna, as I'm learning more, I'm gonna be looking for information about how I could do something like that. So my learning can have purpose. So when I'm learning, I'm not just learning random stuff. I'm learning what I need to learn in order to build something. Not exactly that. I really like the I like to start with something very basic because I wanna limit noise in terms of I want to be able to pick up the concept, and the more complexity that you put in there, you know, makes it more difficult. I'd rather start with something very basic so I can wrap my head around the basic fundamentals of the concept. And then from that platform where I have a good understanding of the fundamentals, refine it to where I dive deeper and deeper and deeper. So for this kind of project, I would much rather attempt a automotive ethnicity project where I could identify which car made just pretty much put any car in there and it tells you which country. It doesn't know which car it is, but it knows which country just based on design aesthetic. And that'd be very interesting to have a program be able to recognize. I mean, well, can we do it? I mean, people know what a BMW is because they know the actual BMW car, but do they recognize? Of course they do. I mean, come on, look at the BMW grills. Who wouldn't be able to recognize a BMW grill? Like no logos, no nothing. No other car has a grill like that. And other little features, yeah, of course. So of course the program can do it. A lot of work. How would you use something like AWS to do this? Basically, from my understanding, you would basically run your program you'd run this program on their servers. So they would give you access to some server, or I guess it'd be a virtual machine essentially, and then you would have to deploy your software on that server or servers, and just run it. And if it's complex enough, I mean, maybe it might take a couple of days or something. You know, but if you try to do it on your own computer, like a computer like mine, an i7 processor, maybe instead of a couple of days, maybe it's like weeks, depending on how complex the project is, or months. I mean, from a business standpoint, you know, waiting weeks just to generate some data so you can actually be able to test your models, which you're testing them, so you don't even know if they even work, right? So that's kind of stupid. You want to get going. You can't have a project sitting waiting on your computer. So it'd be worth the money to pay for the services so that you can get stuff done quickly, because obviously while you're sitting around twiddling your thumbs, your competitors are using cloud-based services to you know, pass you up. So yeah. Also, I gotta explore more of this Google stuff, but I think the way, don't quote me on this, but I feel like Google has some architecture where it's API based. So that being the case, I would assume that you write your program and you can actually technically run it on your own machine. And then you send API calls to their machine learning neural networks or whatever they have, and then they would process it on their hardware. Of course, you're paying for this. It's a service, right? They would process it on their hardware and then spit out the results back to your application. So you basically build a front-end GUI for you to interface and send the calls to their API. I don't know, I haven't built something like this before. I don't know how it works in terms of where the data is stored. I mean, I don't know how that works. I mean, if I have my front-end program that I interface with locally, and I have my data locally, but then the actual algorithms run remotely in the cloud infrastructure, Does that make sense to be? So you say, if I send a request that says, take access these files on my local machine via the network and process them using this algorithm. So then I send that request, it receives those instructions, loads up this algorithm, and targets the files in my local machine. So now it's sending network requests to my machine, read requests, so read file number 1. So it accesses that file, transfers it locally so it can look at it, and then runs the algorithm on it. So it's processing it, scanning, output the results, get the next image. I think that makes sense because most of the time, I mean, not it makes sense or not make sense, but it wouldn't be ridiculous because what's taking the time is the processing of those images. Then again, I don't know how fast this process can be done, because if it's fast enough, then you're introducing unnecessary latency. Because if it's able to scan like one image in a fraction of a second, then that's sloppy programming where the amount of time it's going to take to access sending these read requests over the network, that would slow down the overall. See, the only way that would make sense is if it takes so much time processing each image that the read time or access time is negligible, especially when you can queue that up to where you can, while it's scanning one image, you can load the next one. So there's no delay. As soon as it's done processing the first image, the next image is already there, and so on and so forth. So there's no delay. And I suppose you could maybe even use a similar model to mitigate those latency issues I was concerned about in the first place, where it would buffer things. So it would load like 500 images at a time. Send the request for the first 500 images. Okay, 500 images are now local, and now it's just scanning. Scan. Halfway through, load the next 500. So therefore, basically no latency. The only thing is, okay, I was gonna say, why would you do that in the first place? But if the architecture is such that you're just plugging into an API where you're accessing their algorithms and as opposed to you actually having like a virtual machine where it's like, okay, now this is like a computer that you can access, kind of. So you have a local environment where you could have your program and you have your files and like that's a different setup than me just using some kind of API. Well, you got me thinking how we were doing it. Like we had an API for our customers to use. The customers were sending us data stored locally. Well, it's a different way. We weren't doing machine learning. Our program was trading related, so we were just processing trade reports. So all this buffering and stuff wasn't really relevant. But I think because of that, they were probably sending everything. So they would probably send over this sort of record that our system would load up and process and handle and do different things with it. Yeah, that's a different sort of situation. We have a lot in common. I like cars too, man. Yeah, I love cars, man. I love cars. I love motorcycles. Lamborghini for life. I got my Ferrari over there that I crashed. Fell off my desk. Well, actually, I got the windshield right here. This is a Ferrari 360 Modena. The windshield. Probably can't see it, but there's a windshield. Yeah, I love cars, man. Love it, love it, love it, love it. Do I have my car video on here? See. Gotta love the ladies, man. They are interesting, to say the least. Keep off. What is this? Leave me alone. Go away. Can I just look at my images, please? Jeez. Talking about, do I want to download backup mumbo jumbo? What do you think, man? Oh, we can't even see it. Whatever. Beautiful, but busy as hell. Where is it? Go away, iPad. I think I offloaded a bunch of images, so they're not even on here anymore. Isn't that cute? Guys, you can't see nothing. Well, what is this? Oh, that Maserati. Nice. What's going on? Maserati. Mazzy. Yeah, I think I deleted it. But whatever. This is me. I know you can barely see it. This is me on my motorcycle. Horrible. You can't even see that. Yeah, that's a, you know what? That's a waste of time. You can't, it's too small. You can't see it on that small screen. Store your data in AWS RDS. Yeah, a EC2 instance. Man, people don't pay attention to the details, man. So one of the things I want to do first, before I do any of that stuff, is I want to build something. I want to build some classes, automotive related classes. So when I say I mean like class files. Sure, like, do I want to build like a, I suppose I could build like a Lamborghini Aventador. Build a class for it. And then I could instantiate create an instance of this car. And I could specify the color, the trim, or whatever unique features. Yeah, I want to do something like that, just as a practice. Something cool. So just create some kind of a like Aventador class. So, for example, every Aventador has 2 doors, right? So we would initiate that as a default property. It's got 2 doors. They all have V12 engines, but they would be different V12 engines, but it'd all be 12 cylinder engines. They all have scissor doors. Right? And then I don't know if there's a way to limit the colors. Do I have a list of colors to choose from? Something like that? I don't know. I have to spend some time and think about it. Anyway. Oh yeah, I don't have any complaints in the. Well, I do have complaints. I don't have any complaints in the physical department. Yeah, I mean, I've had good success. I mean, I'd stopped dating for a long time, and one of the first women that I went out with, and we had a wonderful date, used to be a model. Amazing. Unfortunately, she was looking to have a baby like yesterday, so that was a little bit of an issue. And her age, like she needed to have a baby like yesterday, and I was not about to. Yeah, you don't want that. I don't want I'm not rushing into that, and I don't want to waste her time. So, yeah. And then 2, this woman I was dating not too long ago. Oh my goodness, she was. Yeah. So the problem is not physical, it's personality, man. It's consistency, communication. Like right now I was talking to one who she works in aviation, and it's crazy, man. She's always flying, and she's here, she's this state, that state. I'm like, when's the last time you went on a date? And she says, last summer. I can't, man. She looks amazing. She looks great, but what am I supposed to do with that if she's just not available? All right, man. Good to see you first, last. I need to jump off myself anyway. But I am out. This is the Computer Programming University, where learning is always fun, as it should be. Ciao.
With options, your entire strategy is based on what I'm going to give you the fixed protocol. Click subscribe, then click the bell. Click the bell, because you don't want to miss out on more awesome content that I'll be posting soon, right here on this channel. Welcome aboard. Buongiorno, salut, vigets, bienvenidos, hasta luego todos. I'm so excited that you decided to join the team so we can learn together, grow together, and achieve our dreams. Let's do it. See you soon. Grazie. Learning. We gonna do some learn.
I'm telling you.
Guten Morgen. Dobre noche. Buenos dias. Hasta luego. Bonjour. Salut. Begits. Ciao.